Alright, here we have a thing I got from eBay, and it is a transistor curve tracer. And of course, if any of you are into electronics and you understand what a semiconductor curve tracer does, it allows you to measure and match transistors and semiconductors and to test them. Now, Tektronix Corporation, the fine purveyor of oscilloscopes, also makes, or used to make, a line of curve tracers. And even a used one can be thousands of dollars if you get a good one that works. And even to get a broken one that doesn't work and have to repair it, which is very difficult, can be $1,000 or so. So this was something I picked up on eBay, and not including the little transformer, which I got separate, this whole thing came to like $20 or so on eBay. And it consists of the curve tracer circuit itself, which comes like this with these instructions, and comes with a little power supply that matches it. And you assemble the little kit, and it comes with these nice instructions that shows you how to use it, how to connect it. So if you look here, a little schematic. And of course, I'm sure this isn't going to work like a multi-$1,000 Tektronix, but even if it works to the point where we can, that we can plot out some transistors and match them, check their breakpoints and so forth, I think this will be a handy little device, especially like the last project we just did online, the SX450 Pioneer receiver. It doesn't have a DC balance adjustment and it doesn't even have a bias adjustment. So the matching of the transistors in that type of instance would be very important, because if you had a set of transistors that were too far mismatched from one another, and when they make transistors, even though it might be the same part number, they're all a little bit different. They all have a tolerance. So the idea is to find two of them that were manufactured that came out with very, very similar performance specs. And the only way you can do that is to test it with this type of device. So if this works at this cost, it would be a great little addition to the test equipment that we have here. So I thought for the $20-some it costs, it would be a fun project to build, if nothing else, and a nice learning experience. So we're going to assemble this, and I'll have you walk along with me as I do that. I don't have a case to put this in yet, but I'm sure we can make something up. You don't really need anything fancy for this. It's a piece of test equipment. So let's just start and see where this ends up. So I'm going to get everything out and we'll start putting things together. Alright, taking this out of the bag, the first thing I noticed was a couple of things I don't like. If you look at this very lightweight voltage regulator, these are a 7815 and 7915, which is a positive and negative 15 volt regulators. But if you notice, they're totally made of plastic. Not very good conductor of heat. These are very cheap, low-end ones. And the funny thing is, they actually give you heat sinks, but a heat sink isn't going to do you a whole lot of good with a plastic case like that. So I had some new old stock RCAs regulators, and if you notice, they have the traditional metal cases. They're rated at the full 15 watt, which is 15 volt 1 amp, and they're very sturdy, very reliable. So I feel a lot more comfortable using these parts here than using these old cheap plastic ones. So I think that's what we're going to do. The other thing I noticed is these are not the world's greatest capacitors. They're 85 degrees C. They'll probably work for what we're doing. They're rated at 35 volts, so which is more than double of the 15 volt supply. But again, I would probably prefer to put a little better quality 2200s, which something closer to like this. So we have some of those. I may have some 35 volt ones? Yeah, I do. So there's some 2200 at 35s. So I think we're going to use those instead. A little better quality. And these are 105 degree rather than the 85 degree. They'll just last longer. Again, it's a piece of test equipment. You want good components, nice quiet power supplies, and so forth. This would probably all work out of the box. But, you know, if you can afford the couple dollars for the better components, you're better off doing it up front. So, this is pretty much everything here, so we're going to just dig in and start putting things together. Okay, so we have this all soldered up and put together. Turned out pretty good. So I've hooked it up to just a little couple of 100 ohm load resistors. Put it under a load. I have the transformer hooked up. You can see right there. Connected to some leads. And we're going to plug it in. There's our load resistors here and here. And let's plug this in and see what we get. So right now I'm hooked up to the positive 15 volts. So there's plus 15, and it's 15.0. And move over to this one, minus 15, minus 14.97. So I would say that would be a success. So the power supply is all together and ready to go. So, alright, now on to the main board. Little side note on this board, a couple extra things I did was I put heatsink compound and insulators on this. It didn't come with any insulators because those other ones were plastic, which I don't think were going to hold up as well. So I did insulators and heatsink grease, and then I was able to, they already had the holes drilled for these, but they needed to be insulated from the tab on the regulator, because the regulators actually, these tabs are actually live. So I found a couple of screws that fit and screwed this in there so it's nice and sturdy. And the other things that I did was, these are 105 degrees Celsius capacitors, much, you know, higher than the 85s that came with it. And these are 125 degrees Celsius because they're like right up against those heat sinks. And I figure if these are going to get warm, they're going to warm up these capacitors, and that could shorten the lifespan of the caps. So having these high temperature ones will really, really extend the life of this power supply. So I think it'll last a really long time without failing. Okay, little update here. I just started putting this together, and I noticed there were 4 of these little 1N, what were they, 5234s. And if 1N 5234 turns out to be a 6.2 volt half-watt Zener diode. And I thought that was kind of strange the way they were going into the board. So I looked on the little schematic that came with it and found that what they're doing is they're putting 2 diodes in parallel. 2 here, 2 here. And the reason that they do that is to handle a higher current. Now, we're taking 15 volts and we're dropping it down to 6.2. So we're cutting that voltage in half. And then you have this 1K resistor here. So I think they were afraid of the half watt wouldn't be enough, but they didn't want to, you know, they probably had the half watts available and didn't want to go to a 1 watt. So they did that. But this is a bad design. Whenever you put Zener diodes in parallel, the dominant diode, the one that's got the slightly higher voltage, will be dominant, and it will, or slightly lower voltage, I'm sorry, it will clamp off all the voltage, and the other one won't. So really, it really doesn't do you any good unless they're perfectly matched, and even at that, if one of them drifts a little bit, or heats a little bit more than the other, it'll take over and it defeats the whole purpose. So this is a bad design. So I rummaged through my things and I found a couple of the proper 1 watt 6.2 volt diodes, Zehners, and I soldered those in, and then I just plugged off the holes for the extra ones in there. And I think that's going to be a lot more reliable, stable circuit than the way they were doing it. So sorry, but got to deviate from the design a little bit. So just wanted to give you that update, and we're going to continue on and start populating all these components. Okay, we have this all put together, and I have it all soldered up. Have the power supply connected to the board, just laying on here. And what I'm going to look at here is the output, what I believe is the output of this generator, which is right here. And I'm not sure which side of the resistor I want to get on, but I'm going to get on this 10 ohm resistor. And what we should see right here is some sort of a waveform, probably either a sawtooth, triangle, sine wave, something like that. And eventually what we're going to do between these two is we're going to make like a stepped waveform out here that's going to cause the patterns so we can look at our transistor characteristics. So anyhow, let's put this on and see if this thing generates a signal. Alright, so let's move up to the scope. Let's see what we get. Alright, plug in. And looks like we're getting just a regular triangle waveform there. So that's good. Let's go to the other side of the resistor. See what we get. Same thing. There we go. That's good. So our transistors are working. So that's a good sign. Alright. And if I look, and this is what goes to our scope. Alright, so now I want to take a look at what is being generated on our output that's supposed to go to our semiconductor. So let me get figured out here and we'll be right back. Okay, let's see if we can get on this without shorting things out. And I'm generating a lot of noise here holding the probe on, but basically there is the drive signal for the base, and you're not seeing it very clearly because it's not locking onto it very well, but so we have the drive signal for the base of the device in test. And if I look at these other ones, there's the triangle. So between that ramp and the triangle, that's what's going to give you your stepped waveform through the transistor. And that, to my understanding, is what allows the Lissajous pattern, or whatever you want to call it, on your scope, the XY pattern. So I'm pretty confident this is working, so that's good. And I have a case that I'm actually starting to put together, and I just put some paint on it, made it out of aluminum and wood, just a quick one. And here's what we're going to do. I'm going to put some feet on it, and then there's 2 switches that have to be in there, and those 2 switches go for the where's our jumpers at? They actually have a jumper right here, J1 and J2. Those are actually going to be replaced by switches. You can see they're actual jumpers on the board, but we're going to, there's actually little terminal strip, if you look here, there are little holes there, eyelets, where we can put wires, And we're going to run little wires, and we're going to put switches so that we can switch between NPN and PNP type transistors. That's the first jumper. The next one is to switch between low power and high power transistors, so the small transistors and power transistors. So we're going to put those switches on the front panel. We're going to put our X and Y scope output BNC jacks on the panel. We're going to put an on-off switch. We're going to wire in a little LED for power on indication. And then we're going to have our 3 little banana plugs for your device under test. And that way we can plug these little these little hook clips. And I'm actually going to possibly shrink these wires down a little shorter so they don't create as much noise. And that should give us a finished product. We can test it out. So as soon as we get the case done, we'll be back. Okay, I finished wiring this thing up, and you can see it turned out pretty good. So we have power cord coming in, got our transformer mounted, fuse holder, have the main board here, have all the switches wired up. You can see there. This switch here goes between large transistor and small transistor. So when it's flipped up, it's for power transistors, which is what I have connected right now. You can see it's a 2N3055 NPN. And this one here is for NPN and PNP switching. Got a LED on indicator. We have our emitter base collector input wires and our X and Y. X is on the bottom, Y is on the top. I still have to put the labels on here with my label maker. And it's going up to my oscilloscope. And the scope is in XY mode. Now, if any of you have never heard of XY mode, when you turn your seconds per division, your time knob, all the way, so right here, time knob, all the way to the left, if you notice on most oscilloscopes, you'll see a little area at the very end called XY. Okay, see if we can zoom in on that a little bit. See where it says XY? And what that means is when you apply a voltage, so at first you get just a dot in the middle of the screen. You can see it there. And I'm going to turn that down so it doesn't burn my screen. Basically, putting voltage on this will make the voltage change in the x-axis, and putting voltage on this terminal will make the dot deflect in the y-axis. So basically, you're controlling the position of the dot with those two inputs on the x and y axis. Now that's exactly what this is doing. By applying basically a staircase signal to the transistor, we're able to trigger the transistor to function at different levels. Now, when you're in high power mode, let's back off here a little bit. When you're in high powered mode, there are 8 steps from 0 mA all the way up to 2.24 mA. All right, each step. And when you see this pattern here, each one of these lines represents one of those steps. When you're in low power mode or small transistor mode, these are the microamps that each one of those lines represents. Okay, NPN is going to go up, PNP will go down. All right. So if I turn this on and I turn my intensity up, you can see these lines here. Okay, starting with 0. Okay, and we zoom back in. So we start at 0. This next line, since we're in high powered mode, is 0.32 mA, 0.64 mA, 0.96 mA, 1.28 mA, 1.6 mA, 1.92 mA, and 2.24 mA. Okay, so basically when we apply that much MA to the base of the transistor, okay, that's showing us where the knee point is, where that transistor is turning on. Now, if we have a known input, okay, for instance, if we take the very last 2.24 MA, when I'm applying 2.24 MA across the base, okay, so that's 2.24 MA of base current on the transistor, then I can take from my 0 point up and measure. I'm at 2 volts per division, okay, and basically with 2 volts per division, 2 volts per division, according to this, is going to be 20 MA per division. Okay, so I go 20, 40, 60 MA. So I have roughly 60 MA is where I'm turning on. And I'm turning on with 60 MA, I'm turning on, or with 2.24 MA, I'm causing 60 MA to flow in the emitter collector. So if I take my 60 MA divided by 2.24 MA, the gain of this transistor is 26.785. The beta is 26.785. That's your forward current gain. Okay. Now, what I did find is this works really well on large transistors, okay, like these big power transistors. Now, I tried originally to connect a little 2N2222 to this, and even in low power mode, they get really hot really fast. So you can't leave this on for very long. That is what I'm starting to see is the fatal flaw in this little design. There's no protection for the transistor. Also, it says directly in the instructions even, if you hook up the transistor backwards, you will burn it up right away. So you have to be extraordinarily cautious that you get base emitter and collector connected properly, and that you do not turn NPN and PNP backwards, because once again, that will immediately damage the transistor. So this one's just a little bit lukewarm now. It's starting to get warm, but so anyways, it does work, and it works really well. I was surprised. You just that caveat, you have to really be careful with the connections and with the switch configurations. If you do it wrong, instantly damage the transistor. Other than that, this is a very good circuit. It seems to work really, really well. So I'm pretty pleased with it. I did make a little top for it just out of plywood. You can see here. So, and I just did a miter joint real quick. Glued it up, rolled some black paint on it that I had left in a can. And I'll put it together, and I think this is going to be a good project. Like I said, once again, the only thing you got to watch is the wiring of the transistors. So I give this thing a thumbs up, especially for the price. It was $24, and if you look up transistor curve tracer on eBay, this little kit will show up, and there's two ways you can buy it. You can buy it with the power supply module and without the power supply module. Either way. For 25 bucks you get the power supply and everything, and I think that's a real bargain. Quality of the parts, not too bad. I didn't like the fact that these they doubled up on these Zeners. That was a bad idea, so I changed that. I went with a little better capacitors because these do get warm, these little heat sinks here. And I did go, one of these BNC connectors was defective, so I had to replace that with a good one. But other than that, it was a really nice little kit. The resistors measured spot on. Everything was good. So I give it a thumbs up, and if you like this video, I encourage you to give the video a thumbs up, and have a great day. Thanks a lot for watching. More to come.